Good day, I am Mergler Pabere.
Good day, my name is Milet Maybe Antonio, and today we will be discussing our study entitled Thermal Analysis on Gelatinization and Retrogradation Process of Ifugao Rice and Pearl Rice Treated with Palm Oil using Differential Scanning Calorimetry. White rice is also the primary dietary source of carbohydrates in Asian countries, specifically in the Philippines. However, due to the removal of husk and bran layers of white rice, it reduces the essential nutrients that is needed in the body, such as protein, vitamin B complexes, minerals, and dietary fiber. It also contains high amount of digestible starch, RDS, and low amount of resistant starch, also known as RS, which causes high glycemic index and increases the risk of having metabolic syndromes, cardiovascular disease, obesity, and diabetes. Digestible starch is digested in the small intestine where it breaks down into glucose, while RS resists the digestion in the small intestine and is fermented in the large intestine by gut bacteria. Negative effects of rice consumption. White rice is a variety of rice that is mostly consumed in the world and in the Philippines. However, rice contains high glycemic index or GI. High GI intake increases the risk of having metabolic syndromes, cardiovascular disease, obesity, and diabetes. The carbohydrates present in the rice are processed as glucose, as such is not suitable for patients with type 2 diabetes or T2D. It was reported that the consumption of white rice in Asian countries is associated with the increasement of type 2 diabetes and obesity. For the objective of this study, the study aimed to functionalize white rice with the addition of palm oil to increase the resistant starch content of rice grains and to determine the resistant starch content of functionalized white rice using thermal analysis. Methodology. Materials and reagents. The white rice samples, long grain rice, Oliver Enterprise Ifugao premium rice, and short grain rice, or the Royal Elephant Japonica pearl rice and palm oil required in this study were all collected in the local market. These rice varieties include short and long grain. In addition, distilled water and a rice cooker were used in the experimentation. All reagents used were at analytical grade. For the preparation of samples, 1 cup of each variety of white rice was measured and placed in the pot of the rice cooker. After washing the rice 2 to 3 times, 1 and 1½ cup of water was added to the long grain rice, while 1 and 3/4 cup of water to the short grain rice sample. 3 millimeters of palm oil were added to the 2 grain samples. The aforementioned samples were then placed in the rice cooker to cook. To ensure that the moisture content of the sample is maintained, the newly cooked rice was placed immediately in a glass bowl with an airtight lid and stored in the refrigerator at 2 degrees Celsius plus minus 1 degree Celsius. The temperature of the refrigerator was measured and maintained using a digital thermometer or the Thermopro TP-50 as well as hygrometer or the Eagle Tech DC-103. Differential scanning calorimetry or the DSC test, TADSC25 was used as an analytical tool to determine the thermal properties of the rice samples. The calorimeter is composed of 2 pans. The first pan contained a small amount of rice sample being analyzed, and the second pan was left empty for reference. T0 hermetic aluminum along with T0 hermetic aluminum lid was used in the experiment. The sample and reference pans were then be scanned at a rate of 20 degrees Celsius per minute from -50 to 160 degrees Celsius. After a few minutes, its thermal properties were then obtained from the computer screen. Moving on for the determination of RS content or the resistant starch content, onset temperatures, peak temperatures, conclusion temperatures, and enthalpy of gelatinization of the rice samples were obtained from the TRIOS software provided with the DSC-25 instrument. These thermal properties were analyzed in order to determine the formation of the amylose lipid complex on each rice grain sample. The addition of palm oil on rice starch upon cooking should obtain dissociation peaks from the DSC analysis to indicate the existence of the amylose lipid complex. The presence of the amylose lipid complex enhances the RS content of the rice starch. Moreover, the increase of the enthalpy was also observed as its value is related to the amount of complex and crystallinity within the complex. For the last part of our methodology, statistical analysis of data, results were reported as mean plus minus standard deviation. One-way ANOVA was used to analyze resulting differences, if applicable. Post-hoc analysis were used to analyze the resulting differences further.
So here we are shown the table for the enthalpy change of long and short grain rice samples at different starch times. The retrogradation of rice can be distinguished through determination of enthalpy change of rice starch granules after it undergoes storage at low temperature. Farouk et al. Stated that the change in enthalpy indicates the transition of starch granules from crystalline to amorphous structure during rice gelatinization. Table 1 shows the enthalpy of complex long-grain rice ranging from 124.07 joules per grams to 156.63 joules per gram, while the short-grain rice sample containing palm oil varied from 152.42 joules per gram to 139.88 joules per gram. The highest enthalpy obtained for the LP sample is at 156.63 joules per gram for a storage time of 72 hours. The repeated long-grain samples were observed to be statistically different from the long-grain samples at day 3. On the other hand, the highest enthalpy for the SP sample is seen at day 0, obtaining a value of 152.42 joules per gram. The enthalpies of long and short grain rice sample with palm oil addition have both diverse trends. It can be observed that the enthalpy of LP increases with storage time, whereas the enthalpy for SP decreases with storage time. The retrogradation enthalpy of the LP sample against storage time showed an increasing trend, wherein day 3 obtained the highest enthalpy. Although the experimental values for controlled long-grain rice displayed slight fluctuation, its enthalpy attained at day 3 was observed to be lower compared to LP. This suggested that long-grain rice with added palm oil that undergoes cooling with increasing storage time a higher resistant starch content. In contrast, the enthalpy of short grain rice with added palm oil, SP, went down with storage time. The delta H in SP samples were observed to be significantly higher at day 0 and day 1, and it was significantly lower at days 2 and day 3 compared to the short grain control rice samples, or SC. Upon reheating the samples, the LP has a notable increase as the first reheating, i.e. 24 hours of storage. The succeeding storage hours was noted to decrease significantly as compared to the reheated LC. In comparison to day 0 of LP, delta H of reheated LP and day 1 decreased respectively. Chen et al. Stated that the increase in enthalpy can be attributed to the formation of a single helical complex instead of a double helical complex structure. Table 1 shows the trend for the short grain rice samples. The same trend was observed for the reheated SP sample at 24 hours and 48 hours of storage. However, at 72 hours of storage, although the delta H of the sample still decreased as compared to the delta H at 48 hours of storage, the change in enthalpy of the reheated SP sample is higher than that of the reheated SP sample. I stated that the gelatinization of properties of different starches vary and depend on the structure of amylose and amylopectin content, as well as on the presence of other components. The gelatinization temperature, i.e. the onset temperature, peak temperature, and conclusion temperature of the rice samples vary, consistent with the data from other studies. Corral et al. Stated that the TP values correlates with the energy necessary to start the gelatinization process. Table 2 shows the effect of the storage time to peak temperatures of LP, LC, SP, and SC samples. As observed, if the peak temperature of the long-grain rice sample with the addition of palm oil varied, decreasing significantly after 48 hours of storage, and an increase was noted after 72 hours of storage. The LC also showed a decreasing trend throughout the storage time of 72 hours. The RHLP had varying TP, producing the same trend as RHLC. The data for the two sets of samples showed an increase in day 2, and a drop in the value of TP was seen at day 3. On the other hand, as the grain increases its size during the cooking process, the TP value of the sample increases as well. Table 2 shows the effect of the storage time to peak temperature of LP, LC, SP, and SC samples. As observed, the peak temperature of the long-grain rice sample with the addition of palm oil varied, decreasing significantly after 48 hours of storage, and an increase was noted after 72 hours of storage. The LC also showed a decreasing trend throughout the storage time of 72 hours. The RHLP had a varying TP, producing the same trend as RHLC. The data for the two sets of samples showed an increase in day 2, and a drop in the value of TP was seen at day 3. On the other hand, the TP of the controlled short-grain sample varies in every storage time. Comparing the TP of the short-grain rice sample complex with palm oil to the TP of the controlled short-grain sample, the data showed a decrease over time, with a minimal increase at day 2. The same trend was also observed on the reheated SP samples, with a notable decrease in every storage hour. On the other hand, the reheated SC sample had the highest peak on day 2 of the experiment, while both day 1 and day 3 had low and minimal TP difference. Overall, both long-grain and short-grain rice samples complex with palm oil suggest a decreasing trend of TP. Lastly, we have the recommendation. This study demonstrated that the functionalization of white rice through the addition of palm oil, as it was subjected to cooling and storage, affects the digestibility of starch, which has important nutritional ramifications. Thermal properties of the two rice varieties, which includes long and short grain rice, showed diverse results from the DSC analysis. The change of enthalpy in the retrograded rice samples indicate the formation of crystallites in the starch granules and relates to the digestibility of starch. As a final observation, the enthalpy of retrograded long-grain rice containing palm oil showed an increasing trend with respect to storage time and attained the highest enthalpy at 72 hours, which was greater than the controlled long-grain rice. On the other hand, the increase of enthalpy of the retrograded short-grain rice containing palm oil compared to controlled was only observed at 24 hours of storage, whereas its succeeding storage time showed a decreasing trend. Therefore, this study concluded that long-grain rice was more reactive in retrogradation and formation of amylose lipid complex compared to short-grain rice, since it contains a higher amount of amylose. In general, starch granules rich in amylose are naturally more resistant to digestion, thus more effective in producing a low glycemic index. The functionalization of rice was also found to be influenced by the physical-chemical properties of rice, the swelling factor, amylose leaching, thermal characteristics, and basing properties, storage temperature, time, and type of fatty acid used. Lastly, we have the recommendation. DSC analysis of the samples for this study was difficult to interpret due to the variation of results of long-grain and short-grain rice sample. A similar study was conducted wherein they used lauric acid or coconut oil for functionalization of rice. They concluded that through the addition of lauric or coconut oil, together with increasing storage time, affect the retrogradation trend of the sample, and thus implying that its RS content increased for both long and short-grain rice samples. In our study, the long-grain samples with added palm oil was also attained an increase of RS content. However, that is not the case for short-grain samples with added palm oil. The physical-chemical properties of rice, storage temperature, time, and type of fatty acid used affects the functionalization of rice. Therefore, further research is necessary for different types of rice in order to determine the amount of resistant starch produced on each variety during functionalization. It is also recommended to conduct a study using different types of fatty acid in functionalization of rice, as the type and amount of fatty acid influences the formation of amylose lipid complex, which affects the digestion of starch. In addition, ideal ratio of oil and water should also be identified in future studies.